Welcome to the fascinating world of reinforcement learning, where we enable machines to learn optimal behavior through interactions with their environment. Imagine training a robot dog. Instead of programming every single step, we can use RL to let it explore, learn from successes and failures, and eventually master complex tasks like fetching a ball. In this realm of RL, policy gradient methods stand out as a powerful family of algorithms that directly optimize the brain of our learner, the policy. This policy is like a strategy guide that tells our robot dog what actions to take in different situations to maximize its rewards, such as receiving pats for fetching the ball correctly. Unlike other RL approaches that indirectly learn a policy by estimating value functions, policy gradient methods cut to the chase. They focus on directly tuning the policy to achieve the best overall performance. This directness offers several advantages. Policy gradient methods are known for their ability to handle continuous action spaces, which are common in real-world scenarios where actions aren't just discrete choices but can involve a range of values like steering a self-driving car. They also shine when dealing with stochastic policies, where the agent can have a degree of randomness in its actions, making it more adaptable to uncertain environments. And imagine you have a robot trying to learn how to walk. Instead of telling it exactly how to move each leg, we can let it experiment and learn from its stumbles. Policy gradient methods take a similar approach. These methods directly optimize the policy, which is a function that maps states to actions. We can think of this policy as a set of rules the robot follows. In contrast, value-based methods like Q-learning focus on estimating the value of taking specific actions in specific states. These methods indirectly learn the policy by choosing actions with the highest estimated values. The directness of policy gradient methods offers several advantages. They are particularly well suited for problems with continuous action spaces, where actions can take on a range of values, like steering a car. They are also effective in dealing with stochastic policies, which allow for a degree of randomness in decision-making, making them more adaptable. Reinforce is a classic policy gradient algorithm that embodies the essence of trial and error learning. Imagine our robot dog again, now learning to sit on command. Reinforce works by letting the dog try different actions and observe the rewards it receives. The algorithm then updates the policy based on these experiences, increasing the probability of actions that led to higher rewards. It's like the dog gradually learning that sitting when it hears the command sit is a good strategy to get treats. Reinforce is intuitive and relatively simple to implement, but it can suffer from high variance in its updates. This means that the learning process can be noisy and slow, especially in complex environments. It's like the dog getting distracted by squirrels and taking longer to learn the sight command. Despite its limitations, Reinforce laid the foundation for more sophisticated policy gradient algorithms. Actor-Critic methods represent a significant advancement in policy gradient methods by introducing a clever collaboration between two key components, the actor and the critic. Think of the actor as our robot dog, eager to take actions in the environment. The critic, on the other hand, is like a wise mentor observing the dog's actions and providing feedback. The critic learns to estimate the value of being in a particular state, essentially telling the actor how good or bad its current situation is. This feedback from the critic helps the actor learn more efficiently. Instead of relying solely on the sparse and delayed rewards from the environment, the actor can now leverage the critic's more frequent and informative evaluations to refine its policy. This collaboration between the actor and the critic leads to more stable and efficient learning compared to Reinforce. Actor-Critic methods have gained popularity for their effectiveness in handling a wide range of RL tasks, from playing complex games to controlling robots in real-world environments.